Hello friends, welcome to the channel of Nammagiri Academy. In this video we shall try to learn multiple integrals. So let me write multiple integrals, and before we dive into the subject of multiple integrals, we shall go through uh, the some of the basics of the integral of the functions of single variable. Okay, so primarily we shall be concerned about double integration, although we are calling it multiple integral. At least in the initial part, we shall deal with the integration of the functions of two variables. So let us first recall what we learned. So in this, while learning multiple integrals, the knowledge of the integration of the functions of one variable is assumed. Okay, fine. So but still we shall quickly recall some theoretical background of this integration of the function of single variable. So let me draw uh, a representative function, something like this. Suppose this is uh, a and this is b, x equal to a and x equal to b, and this is the graph of f of x. Now we want to integrate the function f of x with respect to x. So basically what we want to do, we want to geometrically, what this means is that we want to find the area under this curve f of x that lies between a and b. So this is denoted as integral of f of x dx from a to b. Now in order to find this area, that is the geometrical meaning of this. In order to find this area, what we do is we divide this interval a to b into small subintervals in this fashion. Okay. And now suppose assuming that this is one strip, the sum of the areas of all such strips will be the total area under the curve. But the problem is that how to find the area of every strip. That is one concern, because this is not a rectangle, although these two sides are vertical, exactly vertical, and this is exactly horizontal. This is not exactly horizontal, and due to which we cannot treat it as a rectangle and find out the uh, area of this strip. Had this been a straight line segment, we could have treated it as a rectangle, and then we could have found the area by using the formula for the area of rectangle. But then we take resort to the uh, idea of limits. In this case, what we do is for every such subinterval, let's say for the first subinterval, the breadth of the subinterval is delta x xi. Okay, x1, let's say. I mean, I is in general, it's an index. So in such case, we shall in case of the first subinterval, we shall be calling it as delta x1, but in general it will be delta xi. Suppose the supremum of the function uh, in this small subinterval, let it be capital Fi. Okay, I hope you know what supremum of function is. Supremum is something like maximum, but maximum, we say we use maximum of a function when there is a point where that value is actually attained, whereas we use the term supremum when that there may not be any point where that value is actually attained, but all the function values are approaching that value. So capital Fi is a supremum of the function that is uh, in this um, subinterval delta xi, and delta x, I mean delta xi is the length of the subinterval, and in that subinterval assume that the supremum of the function has value capital Fi. Now um, taking the sum of all such quantities gives us the upper bound on the area uh, of this um, area under the curve. Okay, so this is called as the upper Riemann sum. This is just a revision. So uh, now similarly we can define lower Riemann sum by replacing this supremum by infimum. So now for every subinterval we'll look at this infimum of that function, okay, and let it be small fi, and multiply that by uh, uh, delta xi, where delta xi is the um, delta xi is the length of that subinterval, and this gives us the lower so if you recognize that this capital Fi multiplied by delta xi is in fact uh, is the approximated area of this small strip, rectangular strip, but that is slightly larger than the actual area of this strip, because this Fi is the supremum, the maximum value, not exactly maximum, supremum, but you can say just uh, um, uh, I mean, you can just replace the word supremum by maximum if you are not very comfortable with the word supremum. And similarly, this small Fi is some sort of minimum, and therefore this is the area of this small rectangular strip, which is approximated but certainly smaller than the actual area of strip. So this is called, and so the summation will give us the lower bound on the sorry, lower bound on the area of area under the curve. So this is called as the lower Riemann sum. And now what we do the next is that we uh, let these the lengths we let the lengths of the subinterval approach 0. So this delta xi's approach 0 all these subintervals, and then we look at what happens to this sum. This, if suppose this sum approaches a certain number, and if suppose this sum also approaches a certain number, and if the limit of this sum as well as this sum happen to be the same, then we say that the function is integrable, and that common value of the limit of these two sums is called as the integral of this function, and that we call as fx dx from a to b. So this is what we know about the functions of one variable. Now let us move on to the function of two variables. F, let's say uh, f is from, let's say, R2 to R. Now not every function is integrable, but there is one sufficient condition for integrability, which is that if f is continuous, then it is integrable. Or even if it is even if it is piecewise continuous, it is integrable. But continuity is quite a relaxed condition, so therefore we may safely say that majority of the functions that we come across while dealing with while studying mathematics are integrable. So now let us move on to the functions. So these functions of two variables. So here we shall now look at the function that look like f of xy. Now there is a change in the domain. Earlier a function was defined on R, and therefore we had an interval, and we found out integral of f of x dx in the interval a to b. Now we don't have interval, instead we have a region, because now suppose if we want to draw this domain R2 as in this way, this is x-axis and this is y-axis. So now our domain, instead of being an interval, it will be a rectangle. In fact, it need not even be rectangle, it may be any shape, any closed shape. For example, it may even be circle, but let us begin with this simplest case, which is that of a rectangle, because rectangle can be written as an interval cross interval. So if this is A and this is B, and if this is C, y equal to C and y equal to D, okay, then this rectangle R is a closed interval A to B cross closed interval C to D, and we know how to integrate over an interval in one variable. This will be useful to us, okay. But now the first question is how to define the integral of a function integral of a function of this sort, f of x comma y, which assume that it's continuous, so that it is integrable. Alright, fine. So in the same way as we interpret this integral of function of one variable as the area under the curve, the integral of a function defined on a rectangle, or rather any shape, but in this case rectangle, is the volume of the solid that is formed by the graph of the function on the upper side, and on the lower side it is bound by this rectangle. So if suppose we want to draw, it is a little difficult to draw a diagram in this way, in three-dimensional, but let me try to draw it. Let's say this is z axis, this is x axis, this is y axis. Since it is a function from R2 to R, let's say it is A, B, C, D. This is the rectangle. I have just redrawn this rectangle R over here. Suppose this is A, B, C, D, something like this. Suppose the graph of the function look like this. It is some sort of this sort of a function. then the volume that is formed by this graph on the upper side and this rectangle on the lower side, and all these walls, four walls, that bind this that and that connect these two surfaces, the rectangle and this upper surface. uh, this the volume of this solid is nothing but the integral, which we denote as integral of f of x comma y uh, over this rectangle R. And we earlier, in case of the integration of single variable, we integrate with respect to x, so we write dx. Here we shall write dA. The meaning of dA will become clear very soon. Now let us now look at this R over here. How should we find or uh, um, try to find the volume of some such solid? Okay, so in the same way as we did in case of the function of one variable, we shall sorry. Okay, we shall divide this rectangle R into small sub-rectangles in this way. Now uh, this every rectangle, let's say, we shall index this set of all small rectangles by I, and this area of every small rectangle, let's say, is delta I. Now we know that the volume of any solid is the uh, area of its base multiplied by its height. So now area of the base here, for now, instead of small strips earlier, in case of one variable, here we have small bars. Okay, so we are in fact dividing uh, this solid into small bars, pillars, small pillars, and then by adding the volumes of all such small pillars, we shall get the volume of the whole solid. Now for every small pillar, we shall, to find the volume of that, naturally we shall multiply uh, its base area by its height. Now the base area is delta AI, where delta AI is the area of the small rectangle, and again we do not know the exact height because um, in this small rectangle, the function takes various values, so therefore there is no fixed height that we can multiply to get the value of that small pillar. So what we do is, again we approximate. um, First we multiply by the supremum, and we take the summation over all i's, and again uh, to we also do the same with infimum, where this capital Fi is the supremum uh, over the ith rectangle, and small fi is the infimum of the function value over this ith rectangle. So this is delta ai. Now here delta ai is the area of this small rectangle. Okay, so this capital Fi delta ai gives us the upper bound on the volume of the solid, and small fi delta ai gives us the lower bound on the uh, volume of the solid, because uh, this approximate, both of them approximate the volumes, but this overestimates whereas this underestimates the volume. Okay, now again, as in the case of one variable, we go on making this mesh finer and finer and finer. So we go on making these squares or these rectangles as small as possible, their length as well as width. So this area approaches 0, delta ai approaches 0, and we check what this sum approaches and also what this sum approaches. If the limit of this sum and this sum is common, is if both of the limits are the same, um, and then we say that the integral exists, and we denote it as f integral over r f of x comma y dA. Now why we called it as dA? Because we have actually we have just transported this symbol ai over here, and we have called it as dA. This denotes area. Okay, just notation wise. So now we have built the theoretical background of the double. This is called as the double integration because here we have used two signs, and here the domain is two dimensional, so therefore it is double integral. The question is how to actually compute. This is all right. I mean, we defined it, and we understood that this is the volume of the solid that is formed by the graph and the rectangle and the four walls that bind the two of them, etc., etc. But how actually we can compute given a function? Suppose function is given, let's say so now we are now starting a sort of a new introducing a new idea. Let's say we have a rectangle R which is 0 to 3. So x varies between 0 to 3 and y varies between 0 1. So let me write in this way also. And f that is defined on this region or rectangle R is okay. So what we want to find is integral over this R f of xy dA. So f of xy is x square plus 3y square dA, and how to do it, that is our question. So now a very important theorem comes to our rescue over here. It is called Fubini's theorem. It tells us that this double integrals can be solved by two successive single integrals. How? Let's say we know how to compute single integral. That means the integral of a function of one variable. So how to break it down into two integrals, each of which is a integral of a single variable. That is what this Fluminen's theorem tells us. And once that is done, we can use our rules of single variable integration and solve problems. So let me write this as okay. In general, f of xy dA is equal to, suppose R is, I'm writing it over here, okay, is the rectangle AB cross CD. That means x is varying between AB, y varies between CD. So we can write this as, this is equal to, I mean in so we can first we can treat this f of xy just as a function of y, keeping x as and treating x as constant. Integrate this with respect to y, substitute the values of c and d, I mean find the definite integral by substituting the values of c and d in the final expression after that we get after integrating with respect to y, and then we that will give us an expression in x alone, because now x has been y has been eliminated since the values of y had been substituted by d and c, and then what remains is only a function in x that we can integrate with respect to x dx, and then again find the definite integral from a to b. This order can also be changed. We can also first integrate with respect to x and then with respect to y, but be careful about the limits of integration and the variable with respect to which you are integrating. Since x is varying between a and b, if you decide to integrate with respect to x first, then you should integrate between a and b first. If you decide to integrate with respect to y first, then you should integrate between c and d first, because y is varying between c and d. Okay, so that gives us a very powerful tool, and these are called iterated integrals. Okay, this is double integral, these are iterated integrals, because we do this is an iterative process. First integrating with respect to one variable, and then with respect to the second variable. Just a passing remark, we shall see that in detail in later lectures, but these iterated integrals can be this idea of iterated integrals can be extended to any dimensions. So for example, if you have a function from R3 to R, even then we can do this triple integration. In that case, we shall have f of x, y, z, and with respect to dz, dy, dx, something like that, and then there will be three integrals over here, and there will be yet another third integral, and limits of the integrations also will be that they also will exist over here. Okay, also 4 times, 5 times, as many times as you want to integrate, but for the time being we shall restrict ourselves to double integration, and toward the end of this unit we shall go to triple integration, and we shall not bother ourselves about the of integration of the functions that are of more than three variables. All right, so let us take one or two examples. let us let us solve this problem itself. Integral of r, so r is given to be 0 to 3 cross 0 to 1 x square plus 3y square dA. Now let us keep this AB, so I'm sorry, AB, so here a value of A and value of B are 0 to 3. This is x, so we shall be integrating with respect to x in the end. Before that we shall integrate with respect to y, so therefore the integral in, uh, in the integration with respect to y comes inside. This is the inner integral, x square plus 3 y square. Okay, so here dy dx, remember that this is the inner integral. So let us compute this inner integral first. We need not bother about this 0 to 3 and dx. That will come into play afterwards. Now, as I remarked earlier, while integrating with respect to y, x should be treated as a constant. So this is as good as constant plus 3y square with respect to dy, with respect to y. So the constant integral of a constant with respect to y is ky. So this will be x square y plus the integral of 3y square is 3y cube over 3. So just y cube. Now we shall have to this is the definite integral, so therefore as soon as we finish integrating, we shall have to substitute the boundary value or the limits of the integration. This dx remains unaffected. Okay, 0 to 3 also remains as it is. We shall substitute 1 and 0 for y. Okay, again here don't disturb this x square. We don't have anything, we don't have to substitute anything for x square. We have integrated with respect to y, and therefore substitution of the limits of the integration are for y, not for x. So let us substitute for first x y equal to 1, x square multiplied by 1 plus 1 cube, which is 1, minus x square multiplied by 0 plus 0, so 0. Now this computation is over. Write dx as it is. Now observe that we have got a function in x alone. Y has disappeared. Now we can happily integrate with respect to x. So this is x square plus 1 dx, and this is x cube over 3 plus x, and the limits of integration. So this will be, after substituting x equal to 3, we have 9 plus 3, 12, minus 0, so 12. So that is how we do it. Let us take one more example. Compute 0 to 1, 0 to a, xy, x square plus y square, dx dy. Now here observe that dx comes before dy. So first we shall be integrating with respect to x. This is the inner integral and this is the outer integral. So it's always good to write the limits, or rather the let's say good to write these limits as inequalities. That sometimes makes certain things clear. So here x is varying between 0 and a, so 0 less than or equal to x less than or equal to a, and 0 less than or equal to y less than or equal to 1. Here value of a is not given, that is an arbitrary value. So our answer will be, the answer that we obtain will be in terms of a. Okay, let us go ahead and solve it. 0 to 1, 0 to a, xy. So we can solve this bracket, we can multiply out throughout. So we get x cube y plus, that is what I prefer. You can use your way of doing it. X y cube dx. This is the inner integral and this is dy. Now as I had already said, now here we are integrating with respect to x, so y remains constant, it should be treated as a constant, and then let's see what we get. So x cube y, so y, since y is a constant, it is and the integral of x to the x cube is x power 4 over 4. So x power 4 y over 4 plus xy cube. So x square over 2 is the integral of x, y cube is a constant. So x square y cube over 2, and limits of integration are 0 to a, dy remains unchanged. Zero to 1. Now let us substitute here the limits of integration. A to the power 4 y over 4, a to the power 4 y over 4 plus a square y cube divided by 2, and after substituting 0 everything becomes 0, so we need not write anything. This is dy. So now again, as you can see over here, the final expression is only in terms of y, function y. A is a constant, so therefore that is not a, that is a constant, so we have obtained a function only only a function of y. Okay, so sorry, um, we can directly integrate now. Okay, so this is a power 4. The integral of y is y square over 2, so a power 4 y square over 2, so that is 8 plus y cube. The integral of y cube is y to the power 4 over 4, so a square y to the power 4 over 8. This and the limits of integration 0 to 1. So after substituting y equal to 1, we have a power 4 plus a square over 8, and after substituting minus this expression with y equal to 0, which is 0. So this is the final answer. So I hope the idea of double integration is clear to you, and it is clear how to integrate uh, the functions of two variables over rectangular regions using iterated integrals. Alright, so we shall end this video over here. In the next video we shall see how to integrate over regions that are not rectangular regions. Okay, see you soon. Bye bye.